So we are now through with the moment of inertia for common figures, no? So that is for 2D plane. Now, let's move on to the mass moments of inertia. So we have here the mass. So our focus here are the solid objects that has a width, length, and depth. So by the end of this lesson, you will be able to apply the principles of integration in determining the mass moments of inertia of a given solid. Meaning to say, uh, the tool here that we're going to use is the integration in order to solve for the mass moments of inertia. And secondly, you will be able to apply the principles of mass moments of inertia in determining the total moment, the total mass moments of inertia for composite bodies. So the first part, um, let's focus on a single solid, while on the second part, uh, let's focus on a composite object wherein it comprises of two or more simple solids that are combined together. Okay, so starting with the first um, principle, that is the mass moments of inertia. So when we talk about moments of inertia, we already done with this one. It only talks about the second moment of area. So our interest there is the area, no, the area of a given 2D figure. Whereas in this lesson, our focus is a body that has length, width, and depth. So we're talking about the mass, the amount, no, that contains a certain object. So mass moments of inertia is defined as the product of the mass of the object and the square of its distance from its centroid towards the given axis. Let's say, for example, if we have here a known axis, okay, so let's say this is the axis of inertia, and we have here a cylinder. No, if we have here a cylinder, okay, and this cylinder is parallel to our axis of inertia, so our cylinder here of course has a mass, so mc, that is the mass of a cylinder, and this cylinder has a distance from the axis of inertia towards its centroid. We're going to call this one as rho na lang. Okay, so in our analysis, let's assume that this cylinder is about or has a tendency to rotate around this given axis. Okay, so what would be its mass moment of inertia? So by definition, we can denote the mass moment of inertia as I, so the same sa second moment of area, but uh, to avoid confusion, we're going to have a subscript of m. So I sub m, that is the mass moments of inertia, is just equal to, again, that is the square of its distance, rho square, and multiplied by its mass. So mc, or mass of the object, or mo na lang, so that to be uniform, mo na lang. So as you can see, no, uh its formula is somewhat similar, no, they have a similarity with respect to the second moment of area, because recall in our previous discussion, if you watch the video, the moment of inertia alone, or also known as the second moment of area, let's denote that one as a, is equal to rho square times the area. But for the mass moment, denoted by Im, is equal to the same thing, the square of its distance. However, this time we're talking about the mass. So for the moment of inertia, that is about the area, or this is also known as the second moment of area. However, for the mass moment of inertia, it talks about the mass. Okay. Now for the first part, uh, the dimension here is unit to the power of 4. No, say for example, if this is SI, commonly in meters, so meter to the power of 4. If it is in English, we have inch to the power of 4, or feet to the power of 4. Now for the mass moment of inertia, um, we also have its own uh, units. So let's explore that one right here. But before that, again, um, always remember this rule that the mass moment of inertia, the same thing with the second moment of area, uh, nagdedepende gihapon, no? It depends upon the given axis, because if the given axis is different, no, or in different location sa lahi siyang nga location, then of course you will also arrive a different value of your mass moments of inertia. So again, this concept is dependent on the given axis of inertia. Now, to analyze its dimension, syempre, kay mo na problema, no, for students. So, let's start with the SI, okay, for SI unit. We're going to perform dimensional analysis. So again, mass moment of inertia is equal to rho squared daw times its mass. Now for SI, yung rho, no, this is not density, but this is a distance. So try to distinguish between the two. So we use rho here to specify the distance. So mostly in SI, that is in meters. So we have meter, tapos square, and our mass is in kilogram or gram, so on and so forth. So therefore, for SI, mostly that is kilogram, no? Nag-una ang mass, meter squared. So ito yung dimension for SI. Now for English, no? Or imperial unit, English. So IM equals rho square times the mass. So yung first niyan is yung distance, it could be in feet, I mean foot or in inch. So let's have foot na lang. So foot square, then yung mass, mostly pounds. So we have pound foot square. However, there are some books, no, that uses a different dimension. So what they did is, again, moment of inertia, I mean mass moment of inertia is equal to rho square. Then we have the mass divided by the acceleration due to gravity. So take note with this one. Wherein again, our distance is in feet, gina square, and then our mass is pound, okay? And the value of, I mean, the dimension of our acceleration due to gravity, g, that is equivalent, no? G is equivalent to 32.2 feet per second square. So we have here feet per second square. So merong dalawang feet sa ibaba, I mean sa itaas, tapos may isang foot sa ibaba. So cancel, sana lang mabilin. Now we now have pound foot, tapos the second square below will be ano, will be transferred at the numerator. So pound foot second square. Ito yung common na ginagamit for mass moment of inertia in English units. Again, we have SI and we have English unit. So that is for our mass moment of inertia. Again, that is the square of its distance from the axis of inertia times the mass of the object. Now, let's talk about the radius of gyration. So, the radius of gyration, this is a distance, no, from the axis of inertia to the point at which the mass of the body may be assumed to be concentrated. Say, for example, we have here a given axis. No? This is our axis of inertia. This is our axis of inertia. And say, for example, we have here a very complex or irregular object. Of course, one method of solving this one is to take integration, meaning maglet ta diri og mga small um, rectangular strips, or rectangular prism. Ato na siya gagmayon. Tapos sum up nato, of course, each of these rectangular strip has its own distance from the axis. Let's say this is y1. I mean, this is row. Okay, row 1, and of course another rectangular strips napod siya row 2, tapos another rectangular strip row 3, so on and so forth, and we add that one. Now, to make things simpler, we're going to use a unified distance. Okay, meaning we're going to locate the centermost part of this complex object, and then that that location, the distance of that from that location towards the axis of inertia, we're going to let that one as k, and that k is our radius of gyration, so k, no. And again, the same thing with the same from our previous discussion. The formula again for the radius of gyration is k equals square root of I over the area. So the area here is the cross-sectional area of this complex body. Okay, this one, the cross-sectional area. The moment here, I, represents the moment of area at already denote as A. So that in order for you to get confused with the mass moment of inertia. So if we have I sub A, it means that that is the second moment of area, or the moment of inertia with respect to the area. And that area again is the cross-sectional area of our composite body. Now, we also have another concept, no? We also have the polar, okay, polar radius of gyration. Now, the polar radius of gyration, pwede na to siya matawag as kp, no? So kp is equal to, again, we also discussed the polar moment of inertia, and the polar moment of inertia, we denote that one as capital letter J. So butanin mo J all over, again, still the cross-sectional area of the given body. So again, on the left, we have the radius of gyration. On the right, we have this polar radius of gyration. Okay? So ang GA represents the polar moment of inertia. Okay, so do you have any questions regarding these two concepts na ay pangutana? Okay, wala. So next, we also have the transfer formula. So this one is very useful in dealing with problems involving mass moment of inertia. So um, as a review, again, the transfer formula is a formula used to compute the mass moment of inertia of a solid with respect to another axis of inertia that is parallel to the reference axis of inertia. Mostly, yung reference axis, no, is the centroidal axis. Let's say, for example, we have here a given cylinder, no? We have a given cylinder. So this cylinder, of course, has a mass moment of inertia, no, with respect to its geometric center, or we can call that one as the centroidal axis. Okay? Nana siya dira ay mass moment of inertia. But what if we are going to solve for its moment of inertia with respect to another axis aside from the centroidal axis? Let's say, for example, this is now our given axis of inertia. No? Let's say this is our second axis. So how are we going to um, to determine the value of our mass moment of inertia for this cylinder with respect to this second axis? Okay, so um, now it is now the time to use a transfer formula. So we're going to use this formula, but be mindful, no? According to the rule set by this theorem, so the theorem behind this formula is known as the parallel axis theorem. So according to the theorem, uh, the two axes, so the central axis, or also known as the reference axis, and the given axis should be parallel to each other. Okay? Kailangan parallel na siya. Okay? And of course, they are separated by a distance d. So we have here the transfer formula. So let's start with the transfer formula applied in mass moment of inertia. So yung transfer formula, the same format with the transfer formula applied for the second moment of area. So again, sa second moment of area, or also known as the moment of inertia, the formula is again the moment of inertia at any given axis, which is parallel to the centroidal, is equal to the moment of inertia along the centroidal axis plus the area multiplied by the distance square of these two axes. The same format with the mass moment of inertia. The only difference is this one, no? On the second term at the right, no? On the second term at the right side of the equation. So instead of A, we're going to use the mass. So here, the mass moment, no, IM of the given axis aside from the central axis is equal to the mass moment of inertia, no, along the centroid or along the central axis plus the mass of the object times uh, the distance of these two axes, so denoted by d squared. So this is our general formula for the mass moment of inertia on a different axis aside from the centroidal axis. Now we can also apply this concept on the radius of gyration. That is the radius of gyration of a certain body at a given axis, no? At a given axis is equal to the radius of gyration of the body along the centroidal axis plus the mass of the object, okay, the mass of the object multiplied by the square of the distance. Okay? So, mara na inyuhang kailangan tigamaan. So, next, we're going to derive, no, the generalized formula for the mass moment of inertia for any homogeneous right prism. Now, what is the significance in finding the mass moment of inertia for homogeneous right prism? So the importance of this one is that it would serve as our um, basis in solving for the mass moment of inertia for um, for another geometric solid. Okay, so this is our basis, or this is our reference. So to derive, of course, we are going to draw our um, right prism. So um, any prism. Let's say this is our complex prism as long as it is right. So nana siya height, no? It has a height. And then of course this is the vertical axis. This is also known as the z axis. And then again, when we say right prism, meaning um, every cross-sectional area of the prism is perpendicular to the z-axis. So if you want to cut this prism halfway, so the exposed cross-sectional area should be perpendicular to the z-axis. Say, if we have here a cross-sectional area, no, this one. So this cross-sectional area should be perpendicular to our z-axis. Now, in order to utilize the integration method, so we're going to assign, no, a differential volume. Okay, we're going to assign a differential volume. So anywhere lang on this prism, and see to it that that volume, that differential volume, should be parallel to the axis of interest. So our axis of inertia here is the z-axis. So this is our axis of inertia. So next, again, this is our differential area. So to make it simpler, let's assume that our differential volume has a rectangular cross-sectional area, and then this is also a rectangular prism. So stretching towards the bottom. Okay. So mo ni siya ato ang differential volume. So of course this one has a differential area dA. And again, this prism has a height h. Okay. So aside from the z-axis, of course, we also have our, again, our y-axis, and then we also have our x-axis. Okay. So if we're going to extract the plane, no, if we're going to extract the xy plane class, no, extracting the xy plane to this one right here, say this is our y, this is our x, and this is our complex cross-sectional view of our right prism. So this is our differential area, no? Mo na siya. So this is, again, this is our dA. So this dA, of course, has a distance of y and a distance of x. But since our axis of inertia is the z-axis, so the z-axis is towards the page or away from the page. So mo lang niya itong gidenote. So kailangan we are concerned only with the distance from this differential area towards the z-axis, and we're going to call that one as rho. Okay, so rho is actually the sum of the squares of x and y, because we can create here a right triangle, diba? This is our y, this is our x, this is our rho. So rho squared is equal to x squared plus y squared, right? Now, um, applying the formula, the general formula of our mass moment of inertia. So the mass moment of inertia along the z-axis is equal to, again, the integral of rho squared times the derivative of the mass of this um, small um, volume, okay, small differential volume, so dm. Now, but no, but dm, again, our mass is equal to, that is equal to density, diba? That is density times the volume. And what is the volume of our um, differential volume, which is a rectangular prism? So that is density times height times the area. Okay, okay, that's it. That is the cross-sectional area times the height. That is our volume. So these two terms is the volume of our chosen differential volume. So let's plug in this one in our integral equation. So imz is equal to the integral. Okay, in order for us to avoid confusion, no, because we already use rho for the distance, so let's use gamma na lang, and gamma again is used to represent the density of this object. So gamma. Okay, so plugging these variables, so we have rho square, the mass is gamma, then times the height, then differential area. Now the gamma, okay, or the density and the height, both are constant, so we can factor that one. So im with respect to the z-axis is equal to density times the height, integral of rho square, tapos times the differential area. Now if we're going to um, integrate this one, no, if we're going to integrate this, or kung imo manotice, no, this one right here, no, this one, ito na expression, actually this is the polar moment of inertia. This is the polar moment of inertia. In our previous discussion, the polar moment of inertia J is represented by the rho square derivative of the area. Okay, so therefore the result would be the density times the height times the polar moment of inertia of the right prism. Okay, so J. Next is um, we're going to ano, this one also. Okay, the J, actually we can replace the J, no, but J, which is the polar moment of inertia, is also equal to the area of the object times the polar radius of a gyration, no? So again, kp lang ni siya to represent that this one is the polar radius of uh, gyration. So if we go back to our the previous slide, so this one, no, kp equals the square root of GAAC. So if we're going to simplify this, so mahimo siyang kp square times the cross-sectional area is equals to JA. Okay? No? So, same lang. Muna itong gigamit. So, going back here, don't forget to write GA. to avoid confusion. So therefore, our moment of inertia, I mean mass moment of inertia of this homogeneous right prism is equal to the density times the height times the area, and then kp square. Again, kp square is the um, polar radius of gyration. Now, going back again, this is AC, or the cross-sectional area. So if we try to analyze the figure, no, the volume, okay, but the volume of this entire homogeneous right prism is just, again, is just the area, or the cross-sectional area of this right prism times its height. Okay, no, and we all know that the mass is just equal to the density times the volume. So therefore, we can reduce this, no, that is the moment of inertia of this object along the z-axis is just simply equal to the mass m times the polar radius of gyration squared. This is the generalized formula for any homogeneous right prism. So do you have any question? May pangutana? Okay, so wala. Proceed ta, no? We're going to find, or we're going to formulate a formula for the mass moment of inertia for both solid and hollow cylinder. So let's start with the solid cylinder. On the figure, we have a solid cylinder with height h and r as its radius. So again, the geometric center, we're going to consider this one as the axis of inertia. This is also known as the z-axis. Okay, as you notice, no, the solid cylinder is an example of a homogeneous right prism because the cross sectional area at every point, no, is perpendicular to the axis of inertia, perpendicular to the z axis. So therefore, we can use, no, we can use the general formula. So use the general formula for mass moment of inertia for right prism. Okay, so again, the moment of inertia, the mass moment of inertia for any right prism along the z-axis is equal to the mass of that prism, no, times the polar radius of gyration squared. Okay, so here um our goal is to solve for the mass moment of inertia of our cylinder. So C lang take one. Sub Z pa gyud, that is along the z-axis, is equal to the mass of the cylinder times its polar radius of gyration. So the problem here is to determine the polar radius of gyration. So from the formula that I have just shown to you from the previous slide, no, but our polar um, radius of gyration is just equal to the polar moment of inertia of the cross-sectional area divided by the cross-sectional area of our given solid. Or to eliminate the square root, so we can also say that kp square is just equal to the ratio of the polar moment of inertia of the cross-sectional area all over the cross-sectional area of the cylinder. So pasabot ani asa man ang cross-sectional area. So this one right here, this shaded part, this is the cross-sectional area of our cylinder. Again, the shape, no, or the figure of our cross-sectional area for cylinder is a circle. So this is a circle, and we already know the polar moment of inertia for a circle. So again, this is and going to put and GA, that is for the circle, is equal to, if you can remember, pi r to the fourth all over 2 na lang. Okay, so that is for the polar moment of inertia for a circle. Now, what is the cross-sectional area of a circle? So the cross-sectional area of a circle is just pi r square. So substituting these values, we have, okay, we have here kp square is equal to 1/2 pi r to the fourth all over pi r squared. Cancel yung pi, cancel dalawa ng r, dalawa na lang sa itaas. So that would be equal to r square all over 2. Again, this is the polar radius of gyration for the circle as the cross-sectional area of the cylinder. Next, solving for the mass moment of inertia of this cylinder along the z-axis is equal to, again, the mass of the cylinder times its radius of gyration square. So the radius of gyration is r squared over 2. So we have 1/2 mass of the cylinder times the given radius square. So this is, okay, this is the general formula for a solid cylinder, no? Or the general formula for the mass moment of inertia for a solid cylinder. That is 1/2 times its mass times the radius square. And what would be the mass of the cylinder? Again, the mass of the cylinder is just the density of the material that uh, comprises this cylinder times the cross-sectional area times the height. Or if ato ni siya expand, the cross-sectional area is again pi r squared times the height. Okay, so again, please take note of this formula. Okay, do you have any question? Class, nakasunod ra? Okay, so proceed sa next. Now, let's try for the hollow cylinder. So still, we're going to use the formula for right prism. For the right prism, again, we have Im z equals the mass of a given prism times the square of its polar radius of gyration. So here, we're going to solve for the moment of inertia. So again, this is our axis of inertia. Axis of inertia. This is also known as the z-axis. So we have the mass moment of inertia of the hollow cylinder along z. So mhcz is equal to, again, the mass of the hollow cylinder. Okay, ato i-reason kay medyo hindi klaro. So hollow cylinder times its polar radius of gyration. So again, the hollow cylinder is a right prism because its cross-sectional area. So this is its cross-sectional area. Okay. So the cross-sectional area is perpendicular to the axis of inertia. Okay, so again, but we have Kp square is equal to the ratio of the polar moment of inertia of this hollow cylinder and its cross-sectional area. And the polar moment of inertia of this hollow circle, so this is a hollow circle, no? So nagana na siya, na siya ay buho. So we're going to use the composite, no, nga rule in finding the polar moment of inertia. That is the polar moment of inertia of the outer circle minus the polar moment of inertia of the inner circle. So for the outer, we have pi times the bigger radius, r to the fourth, all over 2, minus yung inner natin is pi r to the fourth, all over 2. Now, factor out pi over 2. Now we have pi over 2, and then we have r to the fourth minus small r to the fourth. And we can simplify this further, no? Pwede naman to siya ma-factor into r squared minus r squared, okay? Multiplied by r squared plus r squared. So, hindi na lang natin to i-simplify or i-factor out completely yung r squared minus r squared kasi meron tayong makakancel mamaya. Next, yung cross-sectional area. So, the cross-sectional area of this hollow circle, or we can also call this one as the area of the annulus, no? Annulus may kanani. Annulus. So, we have, again, pi, yung bigger r squared, minus yung smaller r. Okay, so plugging these variables, so we have I, mass moment of inertia of hollow cylinder along z-axis is again the mass of the hollow cylinder multiplied by the Kp square. So that is, we have pi over 2, then we have r squared minus r squared, and r squared plus r squared all over the cross-sectional area. So pi r squared minus r squared. As you notice, pi is common and also r squared minus r squared. So what's left is 1/2 mass of the hollow cylinder times, okay, the sum of the square of the two radius, of the two radii, the outer and the inner radius. So this is the general formula for the mass moment of inertia of a hollow cylinder with respect to its geometric axis or centroidal axis. Okay, and how about for the mass of this hollow cylinder? Okay, this is just equal to the density times the volume of the cylinder. So the volume of this cylinder is the area, the cross-sectional area. So that is pi, then r squared minus r squared, again times the height. Okay, so don't forget this is density. And it depends upon the material composition of the solid. Okay, walay question so far? Class, are you still following? Naka-follow pa? Okay, proceed. Next, for the rectangular parallelepiped. So for this one, again, the mass moment of inertia for rectangular parallelepiped depends upon the the axis of inertia, because this solid has three orthogonal axis. You have the y-axis. So let's say this is our y-axis, and then this is my z-axis. Okay, and then this is our x-axis. So the mass moment of inertia for rectangular parallelepiped depends upon this three given axes. So it could be along y-axis, along x-axis, or along z-axis. So let's have the axis of inertia for our derivation along the z-axis. So let's say this is our axis of inertia. Okay, so assuming that this one measures A units, this is side A, and then this is side C, and then this one, the height is side B. Okay, so the same derivation as what we did sa previous. So we're going to consider this as a prism. So with respect to the axis of inertia, our cross-sectional area here is this one. Okay, kani siya nga area, because this area, okay, or this cross-sectional area is the only cross-sectional area that is perpendicular to our axis of inertia, which is the z-axis. No, if you try to change your axis of inertia into the x-axis, so another cross-sectional area will be created, and that is this one. Okay, the left and the right sides. Now if your axis of inertia is the y-axis, then your cross-sectional area will be the top and the bottom surfaces. Now for our derivation, this time, okay, for today, um, our axis of inertia will be the z-axis. So applying the generalized formula for a regular prism. So again, the moment of inertia of our rectangular parallelepiped along the z-axis is equal to the mass of this rectangular parallelepiped times the polar radius of gyration of the cross-sectional area of our rectangular parallelepiped. No? So, but Kp again square is the ratio of the polar moment of inertia of the cross-sectional area of this rectangular parallelepiped divided by its cross-sectional area. And we all know that the polar moment of inertia of the cross-sectional area of this rectangular parallelepiped, so this is a rectangle, no, with a height of b and a width of a. This is our axis, remember. So therefore, this one, no, the polar moment of inertia is just the sum of the moment of inertia along x plus the moment of inertia along y. So if we're going to expand this one, so since this is a rectangle, don't forget that the moment of inertia along x is just the base. Now for this configuration in our drawing, the base here, ang ubos is labeled as a, so we have a, and then the height is b, so that is b cubed all over. Again, this is along the centroid, so that is all over 12. Now for the y, so along this y axis, so mabali na, that is b a cube all over 12. Now we can factor out ab for both terms, so we have ab all over 12. Now what's left on the first term? So if we factor out ab, yung matira is b square. Now for the second, if you factor out AB, yung matitira is a square. Okay, so this is the polar moment of inertia of the cross-sectional area of this rectangular parallelepiped. How about for its cross-sectional area? So yung cross-sectional area um, ng ating rectangular parallelepiped is just the area of this rectangle, no? That is A times B. Therefore, no? Therefore, yung ating um, polar radius of gyration square is equal to GA all over AC. And that is equivalent to AB all over 12 times A square plus B square all over the area, which is AB. So, may makancel. Therefore, the polar radius of gyration is A square plus B square divided by 12. So, therefore, yung ating mass moment of inertia for a rectangular parallelepiped along the z-axis is equal to 1 over 12 times the mass of the rectangular parallelepiped multiplied by the sum of the squares of the sides A and B. Now, how about for the other axis? So, the same derivation, you can come up the mass moment of inertia of the rectangular parallelepiped, let's say along Y. Your formula would look like this, no? So, what are the sides that involves, no, because that involves in the y-axis? So, we have A and C. So, magiging A squared plus C squared siya dito. And how about for the mass moment of inertia of this rectangular parallelepiped along the x-axis? So, still 1 over 12 mass of the rectangular parallelepiped tsaka yung mga sides na involved for the cross-sectional area that is perpendicular to the x-axis is R, C, and B. So we have B square plus C square. Okay, so these are the mass moments of inertia for our rectangular parallelepiped for the three axes X, Y, and Z. Okay, naay pangutana? Okay, so proceed ta for the sphere. So this is also important because sphere is a common solid, no, that we can see in our surroundings and especially in the industrial karang kuan sector. So we're going to derive the mass moment of inertia for sphere along its diametral axis. So let's say this is our diametral axis, no, this one. So it passes through the center of our sphere, and we're going to label this one as y lang, no, y. This is our, again, axis of inertia. And again, this one also is our x axis. Now, since our sphere is obviously not a right prism, so we're going to use another technique, but still utilizing the integration. So we're going to create a differential volume, no, wherein this differential volume should be parallel to our axis of inertia. Now, in a sphere, if we cut a plane that is perpendicular to the y-axis, no, we can create a kuan. If we cut a small width, no, if we cut a small width perpendicular to the y-axis, we can create a, a small cylinder. Say, for example, we're going to visualize that one. So this one, first cut, then this one, second cut. Assuming that this is a very small cylindrical volume. So, ito na yung cut niya. And then, the height of this cut is, this is dy. Okay, this is dy. And then, of course, the radius of this very small cylinder is x. Okay, because this is along the x-axis. Now, in order for you to visualize this, to look like this, no? Paano siya? Okay, so a very small cylinder. So kana siya gikat siya, no? Wherein its radius is x and then yung height niya is dy. Okay, so the distance of this small cylinder with respect to the x-axis is equal to y. Okay, mayroon tayong y dyan, and of course it also has a polar distance r. Okay, now using the general formula for the mass moment of inertia, so we have the mass moment of inertia of a sphere along the vertical axis, that is the y-axis, is equal to, again, the integral of the square of its distance times the derivative of the mass. Okay, next is, of course, we are going to we're going to determine the its distance. Okay, so that is equal to the integral of yung square and distance niya. I mean, let's start, no, let's start first with the mass. Okay, okay, I mean, mamaya pala yung rho muna. So again, yung rho is the distance. So since this is our cylinder, so yung distance niya is x, so x square, tapos derivative of the mass. Okay, now we are going to we're going to solve for the mass, no, for the mass of this small cylindrical shape. So the mass here, okay, dm, is equal to this one right here is this is equal to the density, okay, density times the area, the area of this cylinder. So the cross-sectional area of the cylinder is, again, this is pi, and then yung r niya is represented by x, not this r, because this r is the radius of the sphere. So we have pi x squared, tapos yung height niya, so that is dy. Now, since yung ating volume is a cylinder, no, at saka in-add up natin yan, yung kanyang final na mass moment of inertia should be 1/2, because we all know that for cylinder, no, for cylinder, the general formula for the mass moment of inertia for a cylinder is 1/2 of its mass times the square of its radius. So we're going to use this formula. So therefore, I m of this sphere with respect to the y-axis is equal to 1/2. So, meron siyang 1/2 sa labas. Integral, yung distance niya, again, don't forget, that is x squared times yung dm niya. So, yung dm niya, density pi x squared tapos dy. Now, constant naman dito si density and also pi. So, we can extract that one out. So, we have 1/2 density pi integral of x squared dy. Again, to know the limits of integration, so you're going to look at the differential coefficient. The differential coefficient is dy, so our limits of integration is along the y-axis. So the boundaries of our sphere is at the lowest part. So the distance from the origin towards the lowest part is, again, this is negative r, and then on the upper portion, this is positive r. Okay, yung radius niya. So therefore, our limits of integration is from negative r to positive r. Now, our x here is not coherent with our differential coefficient. So we're going to find any relation that exists between x and y. So looking at the figure, we can derive a right triangle here. So, diba? So from here, meron tayo ditong ma-derive na right triangle. This one is r, this one is y, and this one is x. So therefore, we can say that x squared is equal to r squared minus y squared. Okay, we have an error, or we have a mistake here. This is not x squared ay. This is x to the fourth because dalawang x squared na dito. So x to the fourth. Again, using this relation, no, we have 1/2. This is density pi integral from negative r to r. Then this is r squared minus y squared. Tapos mayroon pang square dy. Okay. So if we're going to, we can simplify this one, no? We can simplify this integral equation further, no? You can also do it yourself if you want. Unya kay limited na itong time. So this one right here can be simplified into the mass moment of inertia of the sphere along y is equal to 8/15. Okay, 8/15. Tapos we have density, then pi, then r to the fifth. Okay, r to the fifth. Now, para ma-prove natin na pareho sila, we can also let some values, no? Say for example, we're going to use our calculator, okay, to prove that sakto bigyan akong gibutang-butang diri nga values. So assume lang natin na yung r natin is equals to 1 unit and our density is also equal to 1 unit. So start 0.5, shift pi, then yung ating density is 1 unit, tas integral. Then we have here yung r natin 1 unit, so 1 minus alpha x square. Sorry. So alpha x square. Tapos yung r natin again from negative 1 to 1. So the answer is 2/3 pi. So using integration. Now let's prove if equal ba niya sa 8/15 density pi r to the fifth. So 8/15, density natin is 1, we have shift pi, and then we have 1 square. So 8 over 15, 1.67 um 55. Okay, this is not r square, but still this is r5, but what 1 man gyapon, no? So wala problema, 8 over 15 gyapon, or 1.67551. Kaganiha, I think that is 2/3 pi ba? Shift pi. So 1 point, okay. I think diri ang part, it should be, okay, we forgot to square. Basta ang gawas ani is 8 over 15 kani siya, 8 over 15. This is density pi r to the fifth. So what ito na butangan 0.5. Okay, again, this is 0.5. Let's try another value, no? Let's say density is 1.5 lang. Then shift pi. And then we have the integral. So close parenthesis. Again, we have r square. So let's say our r is 1.2. So 1.2 square minus alpha x square. Okay, I forgot to put square diri adapita. So this is negative 1.2 tapos up to 1.2. Okay, 6.2538. So ato na tiga man 6.2538. So using 8 over 15. So our density is 1.5 atong giset. Tapos shift pi, radius na to is 1.2 raised to the power of 5, 6.2538. So therefore, equal ni siyang duha. Now, most of the formulas that we have just derived, no, have kanang mass as one of its variable. So here, let us going to come up a formula that contains the mass of the sphere. So yung mass ng sphere natin, so mass of a sphere is equal to the density times the volume of the sphere. And we know that the volume of the sphere is 4/3 pi r cube. So mag-extract ta, no? So the mass of, the moment of inertia of a sphere with respect to the y, if ato na siya i-extract, this is also equal to 2/5. 2/5 times 4/3, diba? 4 times 2 is 8, 5 times 3, 15. So, babalik din siya sa, sa 8 over 15. So, this is again density pi r cube, and since 5 lahat, so multiply ka dito ng r squared. So, this one right here is the mass of the sphere. So, therefore, yung moment of inertia ng ating sphere along the y-axis is equal to 2/5 times yung mass ng sphere tapos yung radius ng sphere squared. So this is our general formula for the mass moment of inertia for the sphere. Next, yung slender rod naman. Let's say, meron tayong ditong slender rod. Ito yung general figure niya. So ito yung gagamitin natin to derive its mass moment of inertia. So let's say this is its axis of inertia. Again, our slender rod has a length L. Okay, length L. And then, of course, naka-angle siya. Angled at theta. So to derive its moment of inertia along the axis of inertia, we need to know its distance of its differential volume. Now, we can let that ito yung kanyang differential volume, no? This one right here, wherein yung shape niya is a cylinder. So, para siyang cylinder. Ganito. Or a prism. Okay. So, yung kanyang height, assume lang natin dr. Okay. So, meaning, yung distance ng ating differential volume is r. Okay. From this this side that coincides with the axis of inertia. So that distance is r, and again, the thickness of our differential volume is dr, and at the same time, the height of our cylinder na nabubuo, and of course, our rod has a cross-sectional area, and we're going to let that one as a C. Mostly, kapag rod, yung cross-sectional area is a circle. Now, yung ating differential volume, of course, it has a distance rho from our axis of inertia. And ito yung gagamitin natin sa ating formula. So again, general formula for our mass moment of inertia of our cylinder rod, SR, is equal to the integral of rho square times derivative ng kanyang mass. Okay. How can we solve for the rho? Now, meron tayong bubuo ditong right triangle na naman. So, if we're going to extract that one, ito yung magiging kalalabasan niya. This is theta, this is rho, and this is r. Okay? So, using trigonometric identity, so we have sine of theta is equal to the opposite the rho over the hypotenuse, which is the r here. So, therefore, our rho is just equal to r sine of theta. So, we are going to substitute this one. Now, for in our integral, so we have r sine theta square times derivative of its mass. Yung mass niya, yung mass ng ating cylinder rod, so derivative of its mass is just equal to the density times yung kanyang cross-sectional area. Yung cross-sectional area niya is constant times its differential height, dr. So we're going to substitute that one. So we have integral. So this is moment of inertia of the cylinder rod. We have density, then cross-sectional area. We have the sine theta, and then we have the r squared. Okay, this is sine squared theta. Then this is dr. So yung r natin again, magsisimula siya from 0 in this portion up to the length of the rod. So from 0 to L. Yan yung ating limits of integration. Now, we can extract all the constant. Constant po yung ating density. Tapos yung cross-sectional area ng rod. Pati na din yung ating sine square theta. So, we have our sine square theta. So, what's left inside is r squared dr. That is from 0 to L. Simplifying further. Okay, so we have sine square theta. So, rules of integration, magiging r cubed all over 3. That is from 0 to L. Therefore, yung ating moment of inertia for our cylinder rod, we have the density, the cross-sectional area of the rod, sine squared theta, tapos meron tayong L cube all over 3. Okay. So, hindi na natin siya evaluate at 0 kasi ma-0 siya. So, here, we have 1/3 density, the cross-sectional area, sine squared theta times L cubed. Take note, babalik natin that the mass of the rod is equal to, again, yung kanyang density times yung cross-sectional area na at yung entire length niya. Kung isa-substitute natin yan to our formula, this one would become 1/3 1/3 times magiging mass of this slender rod times the square of its length kasi mabawasan na ng L kasi andito sa mass niya times the sine squared theta. Okay? And this is our final answer. Now, if the rod, no? If the rod or if the slender rod is perpendicular, no? Is perpendicular to the axis, yung ating theta magiging 90 degrees, 'di ba? Kasi yung forma niya magiging gano'n na, magiging ganito na. So therefore theta equals 90 degrees, and we all know that sine 90 degrees is equal to 1. So therefore, yung ating moment of inertia, mass moment of inertia for a slender rod that is perpendicular to its axis is just equal to 1/3 mass of the slender rod times the length squared. Okay? So okay, para sa case na ito. So naay pangutana? May question? Okay, wala. So mo na siya ang kanang summary for the formulas for mass moment of inertia of common solids. So kindly familiarize this one because this one is very useful, no? These are kanang generic formulas nga i-plug in there that we can use easily when solving some problems. So we have for the cylinder, for the hollow cylinder, sphere, and the rod. So kindly take note with this one. Okay, so for the composite bodies, the mass moment daw of inertia of a composite bodies is the sum of the moments of inertia of its elements. But the moment of inertia of each element must be referred to the same axis of inertia. Same lang po yung kanyang principle dun sa second moment of area. Let's say, for example, on a 3D space, let's say this is the z-axis, this is the x-axis, and this is the y-axis. Kunyari, meron tayo ditong cylinder, tapos may mga holes dito, no? May mga holes. So, yung pag-solve nito, syempre, yung mass moment of inertia of the composite body along the z-axis is equal to, yung una is yung mass moment of inertia of the bigger cylinder along the z-axis. Okay? So again, i-drawing natin. So ito yun. Okay? Ikakat lang natin dito. So is equal to the mass moment of inertia of the cylinder minus the mass moment of inertia of this tree. So hindi natin pwede i-3 times because yung distance ng kada holes na ito, hindi siya uniform with respect to the z-axis. So kailangan kailangan sisiguraduhin na um, define yung kanyang mga distances. So let's say we're going to label this first hole as hole number 1, this is hole number 2, this is hole number 3, and see to it that yung kanyang axis or yung kanyang geometric axis, no, or yung kanyang reference axis, kailangan um, naka naka-parallel siya sa ating axis of inertia. Ito yung ating main axis of inertia. Axis of inertia. Okay? Ibig sabihin, the reference axis for each of these holes should not be inclined, no? Should not be inclined. Hindi rin siya pwede mag-intersect sa ating z-axis or our axis of inertia. Okay? In order for us to avoid violating the rules of the mass moment of inertia. Again, minus the moment of inertia of the hole number 1. So, ito yung first hole. Minus mass moment of inertia of hole number 2. So, dito siya. And then, minus pa rin sa mass moment of inertia for hole number 3. So, why do we use subtraction here? It's because, as you can see in our composite body, no? May hole siya. So, bali, nakasubtract siya. No? So, kapag nagdagdag tayo, let's say, for example, if we have a cylinder, and then meron tayo dito dinagdag na semi or hemispherical body. So, yung gagawin natin yan is to add the mass moment of inertia for the cylinder and then yung mass moment of inertia for the hemisphere. Okay, so yan yung concept to find the mass moment of inertia for composite bodies. Let's have our first example. The problem states the right circular cylinder is made of steel weighing 490 pound per cubic foot. It is 6-inch long and has a diameter of 24 inches. So 4 holes, each 6 inches in diameter, are unequally spaced around a circle 10-inch in diameter, are drilled from the cylinder. Compute the mass moment of inertia about the geometric axis of the body. Now we're going to illustrate this right circular cylinder. So ito yung ating right circular cylinder. Meron siyang height. Okay, meron siyang height na 6 inches. So 6 inches. And then yung diameter niya is 24 inches. So ito yung diameter niya, 24 inches. And then this is its geometric axis, no? Ito yung geometric axis niya. And ito din po yung ating axis of inertia. Now, meron daw 4. So there are 4 holes that are drilled from the cylinder. So, 1, 2, 3, 4. That is around this circle. And yung radius ng circle or yung diameter ng circle na ito, so yung diameter niya equals 10 inches. Okay, so yung ating 4 na holes, they have the same distance with respect to the axis of inertia. Now, if we are going to draw this one, we're going to draw this. Okay, so let's continue. We're going to use the generalized formula in solving for the mass moment of inertia of this right circular cylinder with 4 holes that are drilled throughout its body. So since these four holes uh, are drilled, so it means that we're going to subtract its moment of inertia from the this larger cylinder. So we have the mass moment of inertia of this composite body along, let's say, we're going to call this one as the z-axis na lang. Is again, this is equal to the mass moment of inertia of the huge cylinder HC along the z-axis minus, so in this case we can say that uh, these four holes have the same magnitude of mass moment of inertia with respect to the z-axis because uh, they have the same distance from its respective center, no, center nila towards the z-axis, which is equal to the radius of this um, circle, no, this secondary circle at the inner part of the cylinder. So we have 4 times the mass moment of inertia of the holes. So we're going to denote that one as holes na lang, okay, along the z-axis. If we're going to draw this, so ito po, 1, 2, 3, 4. Sensya na kung hindi siya evenly spaced. Just to visualize lang, is equal to this one, the huge cylinder. So yung moment of inertia natin ng ating huge cylinder, again, with respect to the z-axis, minus yung 4 na holes. So, 1, 2, 3, 4. So, ito din ay cylinder. Okay. That's it. And yung axis of inertia is the z. So, meaning isa dito ay yung distances nila, no, are equal. Okay. Yung distance nila are equal, that is d is equal to the radius of this inner circle, so that is 5 inches. Okay, so the first thing that we should do is to solve first the huge cylinder, and then afterwards solve for the mass moment of inertia for the 4 holes. So let's start with the mass moment of inertia. For the huge cylinder. Hindi naman talaga siya literally huge, pero ito lang yung parang hindi parang tawag ko sa yung sa main na cylinder. So for the huge cylinder, ito yung body. Okay? Then ito yung kanyang inertial axis or the axis of inertia z, and yung axis of inertia is collinear with the geometric axis of the body. It has a height of h, no? H natin is 6 inches. Then meron siyang radius. Yung radius niya is half the diameter, that is 12 inches. Okay? Yung density niya is 490 pounds per cubic foot. Okay. So again, ito po yung ating analysis. So we have moment of inertia of this huge cylinder along the z-axis is again equal. So we already derived this one, yung cylinder, that is 1/2 times the mass of the huge cylinder multiplied by the square of its radius. Now, yung mass ng ating cylinder is we have the density, tas yung cross-sectional area niya. So, that is pi r squared multiplied by r squared ulit. So, plugging these values, so we have 1/2. Density natin is 490 pound per cubic foot. Tapos, pi times, pag i-combine natin to, r to the 4th, yung labas. So, this is 12 inches. Kailangan po natin siya i-convert into foot. 12 inch per foot. And then to the power of 4th. Again, kapag English, no? English units yung given, don't forget to divide this by the acceleration due to gravity, which is equal to g. Okay, remember that one dun sa first slide. So, divide by g, which is 32.2 feet per second square. Now, unit analysis. So, meron tayong inches. This is cubic feet. Yung result dito is feet to the 4th power. So, cubic feet 4th power, magiging feet na lang to dito. No? And then, yung panghuli dito, we have pound, no? Foot-pound. Again, this is r squared, pi r squared. Okay, nakalimutan natin yung height. Sorry. Meron pa tayo ditong height. H. Okay. So, yung height natin is 6 inches. I forgot to put here 6 inches. So, i-convert natin. We have 1 foot. Tapos, 12 inches. I forgot the height. Again, the mass is density area times the height. Meron pang height dito. So, cancel yung inch. Foot na lang yung natira. So, we have 2 foot. So, cancel yung isa sa ibaba. So, we have pound foot. Tapos, yung second squared, it will transferred to the numerator. So, magiging pound foot second square. So, na-achieve na natin yung kanyang desired na dimension. So, HC along Z. We're going to use our scientific calculator. So, we have 0.5 yung 1/2 times. We have 490. Tapos, times pi. Tapos, yung 12 divided by 12. Sulat na lang din natin. 12 divided by 12. That should be raised to the power of 4. Tapos, meron pa tayo ditong 6 times 1/12. Tapos, divide natin by G, 32.2. Okay. So, the answer is 11.95. So, we have 11.95. This is pound foot dot second square. So, ito yung ating moment of inertia for the huge cylinder. Let's proceed to the 4 holes. Now, sa analysis natin, i-considered natin na the 4 holes are 4 cylinder that is made of steel. Isa-subtract lang natin. Yan yung sa ating analysis eh. Okay? So, for the 4 holes, in our illustration, let's just pick one hole, no? Or one cylinder that represents the hole. Okay, ito po natin cylinder. And then, it has its own axis. However, this is not our inertial axis or the axis of inertia. I-let lang natin as the centroidal axis O. Yung ating axis of inertia, ito yun. Okay? Ito yun. axis of inertia, or nilet natin ito as the z-axis kasi ito yung ating axis ng huge cylinder. So ito po yung ating huge cylinder na naka hidden line, di ba? Hindi lang siya naging sentro. So siya natin na at the center siya. So the distance from the centroidal axis and the z-axis is equal to the radius of the inner circle, which is half of of this diameter, 10 inches. So i-note lang natin as D. Okay? So since we are to find the mass moment of inertia of these 4 holes along the z-axis, so um, it's a different axis, no? Kasi hindi na siya yung centroidal axis niya or geometric axis niya. So since nasa ibang axis na, we're going to use the parallel axis theorem. So this is again for the 4 holes. Now, our parallel axis theorem states that the mass moment of inertia of our holes along the z-axis is equal, again, mamaya na lang tayo mag-multiply by 4. Let's consider lang yung isang hole, considering one hole. So, dito, so the mass moment of inertia of the hole, so hindi muna natin lagyan ng S to avoid confusion. So, yung hole along the centroidal plus again, yung mass ng ating hole times the square of its distance. So, ganun po. Next, yung mass moment of inertia of this hole along its centroidal axis, alam na po natin yan. Kasi this one is like a cylinder. This one is a cylinder, no? And then we already know the formula for the moment of the mass moment of inertia of a cylinder along its geometric axis. That is 1/2 times yung mass ng ating hole times yung radius ng ating hole. So meron tayong ditong radius, small r lang, ng ating hole. So that is r square plus mass ng ating hole. How about yung d niya? So yung d niya, again, D is equal to 5 inches. Yung R natin dito is yung radius ng hole. Given dito yung diameter niya, so automatic this is 3 inches. Okay, so D square. Common po yung ating mass ng hole. So, mass ng hole times 1/2 R square plus D square. So the mass of our hole, or like a cylinder, so that is pi the cross-sectional area, so pi r square times the height. The height of the hole is similar to the height of the huge cylinder, which is equal to 6 inches. So times 1/2 r square plus d square. Now, plugging in the values, so we have this equal to the density 490. Again, we have pound per cubic foot, pi times yung radius natin ng ating hole is 3 inches, so 3 divided by 12 para magiging foot siya, tapos square root, at pati na yung height, naka-inches siya, divided by 12 para magiging foot, tapos multiplied natin by 1/2 yung radius, again 3 divided by 12 para magiging foot, squared plus yung distance is 5 all over 12 foot, and then another squared. Kailangan i-divide natin by the acceleration due to gravity, 32.2 feet per second square. Now dito, feet square tapos feet. So dito ma cubic fit na to dito. So, makancel po siya. So, dito naman sa loob ng brace, square foot. So, meron foot sa baba. So, magiging foot na lang po sa itaas. So, yung natitira na dimension is pound, foot, tapos yung second squared mapupunta sa numerator. So, therefore, the mass moment of inertia of a single hole with respect to the z-axis is equal to, gamit tayo ng ating calculator. Again, we have 490 shift pi, tapos we have 3/12, tapos we have, okay, I forgot to put square, tapos dito we have 6/12, tapos we have 1/2, so 0.5, tapos 3/12 square plus 5/12 square, close parenthesis, tapos all over 32.2. Okay, that is our answer. Okay, so yan yung ating answer. That is equal to 0.306. Okay, so I think meron tayong error dito. So I forgot to put another close parenthesis, no? Kasi dalawa pala to dito. Again, okay. So, i-try po natin. Okay, so balikan natin yung ating calculator. So, tama na po yun. Again, yung answer po natin is 0.306. So, sulat natin. We have 0.306 pound, foot, tapos second square. Again, this is only for a single hole. Now, on the final step, so yung ating mass moment of inertia of our composite body along the z-axis is equal to the mass moment of inertia of the huge cylinder along the z-axis minus 4 times the mass moment of inertia of the single hole along the z-axis. So, for the huge cylinder, balikan natin. So, that is 11.95. So, 11.95 minus 4 times the mass of each hole, the mass moment of inertia of each hole is 0.306. So 0.306, using our calculator, AC, so 11.95 minus 4 times 0.306. So magiging 10.726. So 10.726 pound foot that second square. So this is our moment of inertia of our composite object with respect to its geometric center or along the z-axis. Next, we have our final example. Compute the mass moment of inertia of the cast iron flywheel with respect to the axis of rotation. So the cross section is shown below. The flywheel has 6 elliptical spokes. So ito yung spokes niya, no? Yan yung spokes niya. 20 by 30 mm. So elliptical siya pag ganito yung forma niya. So it has a major axis and a minor axis. Yung kada spokes niya measures 20 by 30, which may be considered as slender rods. So slender rod po to siya, but yung kanyang cross-sectional area, unlike dun sa na-derive natin na circle, dito elliptical. So yung cast iron. So this flywheel is made of cast iron with a density of 450 pounds per cubic feet. Ito po yung mga additional dimensions. Again, kailangan alam mo rin yung mga parts ng ating flywheel. We have first, itong hollow cylinder sa gitna. Yan po yung ating hub. And then, yung outer hollow na cylinder, ito po yung ating rim. Okay, so how are we going to analyze this one? So, based on the illustration, we can say that we have the original flywheel. Sensya na po sa drawing. So, meron siyang 6, no? 2, 3, 4, 5, 6. Tapos may hub sa gitna. So, yung moment of inertia, mass moment of inertia ng ating flywheel with respect to its axis of rotation. So, syempre, mag-rotate siya along this axis. So, dito, ito yung axis of inertia. So, it is where the flywheel rotates. So, again, going back to our equation, the mass moment of inertia of our flywheel is equal to first the mass moment of inertia of our hub H plus the mass moment of inertia of our rim plus, okay, 6, okay, 6 na spokes. So we have 6 elliptical spokes and they are placed evenly around the hub. So 6 times the mass moment of inertia of the spoke. Okay, so ito-drawing natin sila isa't isa with respect to the axis of inertia. First, yung hub. So for the hub, ganito yung hub natin. And then, ito yung ating axis of inertia. So we can treat this one as a hollow cylinder. We already have a formula for the hollow cylinder. Plus, yung rim, still a very hollow cylinder, very huge hollow cylinder. Tapos, meron siyang thickness. Ito yung thickness niya. So, still along the axis of inertia. Yung spoke, so paano yan natin i-analyze? For the spoke, so that is plus. Again, this is our axis of inertia, axis of rotation. Yung spoke natin, naka-elliptical siya. Tapos, meron siyang, syempre, yung kanyang height. So, para siyang rod na naka-perpendicular to the axis of inertia. Okay? Papansin natin, perpendicular siya sa axis of inertia. And we already derived a formula for a slender rod. So, we can solve this kind of problem. So, first is we're going to solve for the mass moment of inertia for the hub, then for the rim, and finally for the spokes. Okay, so this is how we're going to attack this kind of problem. Don't worry, given tayo ng mga dimensions for each part. So starting with the hub. For our hub, I'm going to draw that one. So our hub is a hollow cylinder. Okay. Now, yung given natin, okay, given natin. So, yung inner radius r, small r, so ito yun. And then, yung ating outer radius r, ito yun siya. And of course, meron yan siyang length. Okay, so our small radius is based on this figure is we have 30 as the diameter, so divide by 2, that is 15 mm. Then our bigger radius, again we have 60 mm divided by 2, that is 30. So 30 mm. How about our length? So our length shown below, this one 100. So that is 100 mm. So the mass moment of inertia along this axis, so the mass moment of inertia of the hub is equal to 1/2 the mass of the hub times the sum of the squares of the inner and outer radii. So ano po yung ating mass of hub? So that is equal to 1/2. Mass of hub is density times yung cross-sectional area, that is the difference of the squares of the two radii, r squared minus r squared, times yung height po niya or yung length, times r squared plus r squared. Okay? We can combine this one, no? Sama difference. So we have 1/2 density pi times the length times r to the fourth minus r to the fourth. Okay, di ba? Nako-combine natin yan. So next, yung given po natin na density is somewhat not in line with the given dimensions for the radius and the length. Kasi the dimension for our radii and the length is in SI, however our dimension for the density is in English. So to be uniform, we're going to convert our lengths into feet or into foot. So yung 15 mm, no? So again, 1 inch is 25.4 mm, and then 1 foot is 12 inches. So the same thing yung gagawin natin for the bigger radius and the length. So using calculator, 15 times 1 divided by 25.4 times 12. Yung sagot niyan is in in foot. That is 0.049 na lang. So 0.049 foot. Yung bigger radius, substitute lang po natin dito sa ating equation. So we have 30. So we have 0.0984. 0.0984 foot. Tapos we have 100 mm. So we have 0.3281. So 0.3281 foot. Okay. So next, we are now ready to solve this one. So we have the moment of inertia, the mass moment of inertia of this hub is equal to 1/2. The density is 450 pound per cubic foot. We have the pi, we have the length 0.3281 foot. Tapos yung r natin na laki, 0.0984 to the fourth power minus 0.049 to the fourth power, so automatic feet to the 4. Huwag kalimutan, divide lahat by the g, 32.2 feet per second square. So cubic feet, fourth, so what's left is isa na lang, meron pa sa ibaba. So what's left is isa lang na foot, isang pound, at yung second square, it will be pupunta siya sa numerator. So IMH is equal to, so using our calculator, we have 1/2, so 0.5 times 450. Tapos, shift pi, tapos 0.3281 times 0.0984 to the fourth power minus 0.049 to the fourth power, divide by 32.2. So we have 6.337 times 10 to the power of negative 4. So 6.337 times 10 to the power of negative 4 pound-foot second square. So we're going to take note with this one. Meron na tayong hub. Next is yung ating rim. So for number 2, we have the rim. So ito yung drawing ng ating rim. And then ito po yung ating inertial axis. So still, para siyang hollow cylinder. So yung rim natin, meron siyang inner radius R, tapos outer radius R, tapos may length din siya. Same with the hub. For the rim, given natin the R for the rim, pareho lang po siya sa hub. I mean, hindi pala, sorry. Yung inner radius ng rim is ito, 380 divided by 2. No? So 380 divided by 2, that is 190. So 190 mm. Kakonvert yan natin. So 1 inch, 25.4 mm. Tapos 1 foot is equal to 12 inches. And for the bigger radius, that is half of 440. So that is 220 mm. And then for the length, pareho lang sa hub 100 mm. So kukupihan lang natin, yung length is 0.3281. So 0.3281 foot. Now for the inner and outer radii, so let's start with 190 times 1 over 25.4 times 12. Okay, forget to put point. So we have 0.6234. So 0.6234 foot. And then sa 220, okay, sa 220, type na lang natin ulit 220 times 1 over 25.4 times 12. So we have 0.7218. So 0.7218 foot. Next, we're going to use the formula, no? So same formula for hollow cylinder. So moment of inertia of our rim is equal to 1/2 times the mass of the rim times r squared plus r squared. So same lang sa previous. Kopyahin lang natin to. So we have this equal to 1/2 density pi, tapos yung length, tapos r to the fourth minus r to the fourth. Same lang dito, no? So plug in the values. 1/2. This is 450 pound per cubic foot. Tapos pi, yung length is 0.3281 foot. Tapos yung ating r. So r natin is 0.7218 to the fourth power minus 0.6234 to the fourth power. That is feet to the fourth. Divide natin lahat by 32.2. feet per second square. Okay? So, cancel out cubic foot. Isa na lang dito. Tapos, cancel out sa ibaba. Now, we have the mass moment of inertia for the rim is equals to, so we have 0.5 times 450 times shift pi, tapos 0.3281, tapos 0.7218, tapos raised to the power of 4 minus 0.6234 raised to the power of 4 over 32.2. Okay, syntax error. Okay, we forgot to put here. Okay. Hindi natin na down. So, kailangan natin to i-down. So, down. Sorry. Okay, pati na yung comma. Pati na yung parenthesis. So, minus 0.6234 raised to the power of 4. So, the answer is 0.8672. So, 0.8672. That is pound foot second square. So, mass moment of inertia for the rim. If we compare the value for the hub, as you notice, the hub is much closer to the axis of inertia than the rim. So, again, we can say that there is a significant difference between the mass moment of inertia of the rim and the hub. Although they have the same configuration, naka-hollow cylinder sila, pero si rim yung merong malaking value for its mass moment of inertia because, again, the mass moment of inertia is a function of its distance. So, habang papalayo ka, lalaki yung mass moment of inertia mo. So, kapag nagmo-move na yung ating flywheel, mahirap siya papahintuin, lalo na kapag nakapag-sustain na siya ng rotational speed, lalo na sa rim. Okay, sa rim niya. Kasi sa higher subject nyo, pwede natin ma-relate yung mass moment of inertia sa rotational speed. So, may formula yan. Okay? So, as the mass moves farther away from the axis of inertia, then you have a greater value of your inertia also. Let's have the last one, number 3, for the elliptical spokes. Ating elliptical spokes, if we're going to turn this one, if we're going to turn the flywheel horizontally, ganito yung mangyayari, yung axis of inertia, ganito na. Tapos, ito na po yung ating spokes. I-consider lang natin yung isang single spoke. Okay, ganyan siya. And yung ating spoke, okay, para realistic yung ating drawing, yung spoke natin pala is hindi siya nag-terminate at the center but at the hub. So, kapag ito yung hub natin, yung spoke natin is dito lang, no? Okay. Diyan lang yung ating spokes. So, based on those formulas that I have shown to you for the common objects, we have a formula for a slender rod, no, about an axis at one end, right? We have that formula. So our formula, no, or we can also have this distance. We can also have this distance, this one right here, yung sa middle part niya. Okay, dito. Okay, ito na part. So, ano ba yung distance nito? Yung midpoint ng ating spokes from the axis, okay? From the axis of inertia. Ito natin ito as the axis O, or the centroidal axis of this elliptical spoke. So, yung ating formula for the mass moment of inertia for elliptical spoke along the centroid O, makikita natin to dun sa previous na slide. Okay? So again, yung kanyang cross-sectional area is an ellipse. So dito, wherein ito yung A, tsaka ito yung B. So the A is equal to 30 mm. Tapos yung B is equal to 20 mm. Okay. So, next, yung kanyang moment of inertia. So, the moment of inertia for a single spoke along the axis of inertia. So, let's say this is z axis. So, z lang is equal. So, using parallel axis theorem, it's because we have a different axis rather than the centroidal axis of the spoke. So, we have moment of inertia of the spoke along its centroidal axis plus the mass of the spoke times yung distance squared. So, saan ba ito yung distance? So, ito yun. D. Okay? Isa-solve pa natin yan. Okay, let's continue. So, the mass moment of inertia of the spoke with respect to its centroidal axis, this one right here, which is this axis is perpendicular to its geometric axis. Yung geometric axis po niya is dito, no? So, ito, iba to siya. So, if we look back on our previous slide, okay, ito. So, ito yung cylinder rod about this axis. Yung formula niya is 1/12 the mass of the rod times the square of its length. So, ito yung length niya. Okay? So, balik tayo dun. So, we have 1/12 the mass of the spoke times yung length niya. So, L squared plus the mass of the spoke times the distance square. Factor out the mass. So, mass of the spoke times 1/12 L square plus D square. Now, we need to find the length of the spoke. So, ito yung kanyang length. And this length is the difference of 380 and 60 divided by 2, right? So, L is equals to 380 minus 60 divided by 2. And that is, so 380 minus 60 divided by 2, that is 160. So, 160 mm. Yung distance niya, so yung distance niya, D, from the center is half of this length, okay? Yung D natin is equal to half of the length plus yung radius ng yung outer radius ng ating hub. So, outer radius ng hub, okay? Yun lang po. Akala ko kasi diameter. So, plus the outer radius of the hub. So, we have 1/2. Yung length ng ating spoke is 160 plus the outer radius of our hub is 30 kasi 60 to in diameter divided by 2, so 30. So, plus 30. Therefore, yung ating distance D is 1/2 times 160, that is 80, plus 30, we have 110. So 110 mm. Okay. How about for the mass of the spoke? So dito yan natin i-solve again. Kailangan din natin to i-convert, no, yung ating length at saka yung D. So yung L, ka-convert natin yan into foot. So follow lang yung ating conversion unit. We have 160 times, we have 1 inch, 25.4 mm, and then 12 inch, 1 foot. So equals 0.5249. So 0.5249 foot. For the distance, so we're going to convert na lang, no? So we have 110. Yan. So the distance is 0.36 361. So 0.361 foot. Okay. So next, for the mass. The mass of the spoke is, this is an elliptical cylinder. So density, the area of the cross-sectional area of this one, that is pi AB. That is for the ellipse, diba? Pi AB times the length. Okay? Times the length. So ito yung L natin. So substituting, we have density pi AB times the length times 1/12 L square plus D square. Substituting the values, yung A at saka B natin, need pa natin i-convert into foot. So going back sa ating calculator, so dito tayo, we have 30. So 0.0984. So 0.0984 foot. Tapos yung ating B, that is 20. We have 0.0656 foot. Now our density is again that is 450 pound per cubic foot. So this is for the single spoke lang, no? So i-multiply natin yung sagot natin dito by 6. So again, 450 pound per cubic foot. We have pi, our A is 0.0984 foot. Our B 0.0656 foot. Tapos yung L natin is 0.5249 foot. Tapos times 1/12, 0.5249 square plus yung distance 0.361 foot square. Kalabasan dito is square foot times 1/32.2 feet per second square. So yung lalabas dito is yung mass moment of inertia of the spoke with respect to the z-axis. Okay? So calculate natin. We have 450 times pi times A 0.0984 times 0.0656 tapos yung L 0.0656 tapos yung length is 0.5249 0.5249. So answer times sa loob 1/12 times yung L again 0.0656 5249 square plus yung distance natin, we have 0.361 squared, okay, equals, tapos divide pa natin by 32.2. So we have 0.023. So 0.023 pound-foot second square. Ito yung sa ating spoke. Now, combining together, so for number 4, we have moment of inertia of our flywheel equals moment of inertia of the hub plus moment of inertia of the rim plus 6 times the moment of inertia of the spoke. So for the hub, we have 6.337 times 10 to the power negative 4. 6.337 times 10 to the power negative 4 plus yung rim, we have 0.8672. 0.8672 plus 6 times the spoke, 0.023. So 0.023. So therefore, the mass moment of inertia of the flywheel, we have 6.337 times 10 to the power negative 4 plus 0.8672 plus 6 ka-spoke times 0.023, and the answer is almost 1.006. So 1.006, that is pound-foot second square. So this is the mass moment of inertia of a flywheel with respect to its axis of rotation. So that's it. Thank you for watching, and may God bless you.